In this video, I will derive a formula for beam warming method. We already saw the derivation of beam warming method, but now our aim is to derive it for the case when we have slopes, when we have a slope formula. And you can see that this is the slope formula where we have a slope. When we can put the value of slope over here, this slope value and this is the slope, when we put that value over here and sigma ni, which is slope at cell I, slope at cell I minus 1, then we get the beam warming method. Let me just solve that for you. I already solved it for you, but I just need to explain that. So the first thing is you just need to memorize the or you just need to look at the, don't need to memorize it, but you just need to put the value of sigma ni over here, and then we put the value of sigma ni minus 1 over here. The sigma and I minus 1 can be obtained directly when we replace I with I minus 1. All these terms remain the same. These terms remain the same, and what we do, we simply solve these two expressions, take a difference of these two expressions. After that, what we do, we multiply this equation with this term with the delta x, and this delta x we multiply this with the coefficient. So what we get, when we multiply delta x with this term, we get the following term, and this coefficient will be multiplied with this term again. So we have finally the term given over here. Now we do the same for the second term. We multiply this term with u bar delta t, and minus minus becomes plus, so we have plus over here, and u bar delta t multiplied together becomes u bar delta t whole square, and this delta x and the delta x over here, when they multiply together, we get delta x square, and this is 1 by 2. So this is required to reach at the beam warming method. The next thing is to just subtract, just cancel out these two terms over here, and I think nothing new in this step. And the next step is to take common these two terms. From these two terms, take common u bar delta t by delta x. And remember that u bar is the speed of the wave. So, for example, we have partial q by partial t plus partial by partial x, u bar q is equal to 0. So u bar is the speed. So when we take common u bar delta t by 2 delta x common from here, we get, after taking LCM, 2q and I minus 2q and I minus 1. Then this is, since we have minus outside, so this becomes plus q and I minus 2q and I minus 1, since this has become plus, and we get q and I minus 2 plus This term remain the last term remain the same. So after adding these term, for example, this becomes 3q and I, and adding these two terms we get minus 4q and I minus 1, and finally the last term is plus q and I minus 2, and the last term remain the same. This is the beam warming method. This is called beam warming method. You have seen that beam warming method earlier, and we derive it by using the Taylor series. Here the difference is, in that case, there we just had that U bar. Here it is a scalar quantity, and when we derive it earlier, we took the system, so that's why we have a matrix over here. So this equation for the matrix form is q n I minus a delta t by 2 delta x 3 q n I minus 4 q n I minus 1 plus q n I minus 2 plus 1 by 2. Now we take this outside, a square delta t by delta x whole square q n I minus 2 q n I minus 1 plus q n I minus 2. So that's what we have over here. So this is the beam warming method for the system of equation, and this one is for the scalar equation. Thank you for watching.